All right, everyone, welcome back for week 3. So this week, and in this video, we're going to have the final video on the topic of derivatives. Then the second video for this week will be a video on undoing some of the things we've done with derivatives. Then the 2 videos for next week will kind of be in the similar vein, and then the 2 videos in the following week will be introductory material for Calc 2. Okay, so we're going to talk about what are called indeterminate forms. So there are 7 kinds, and I have them listed here. So what we can broadly think about with an indeterminate form is their limits where, say, for the first example, you have the numerator and the denominator is going to 0. But as we've seen many times, if you're told that the numerator and denominator are both going to 0, that doesn't tell you what the limit is going to be at all. As we've seen many times, the limit with the numerator going to 0 and a denominator going to 0, it could maybe be going to infinity or 0 or something else. And the same is true for any of these other forms that are on here. So for infinity divided by infinity, 0 times infinity, infinity minus infinity, 1 to the infinity, 0 to the 0, 0 to the 0 is kind of different, but it still falls under indeterminate forms, and then also infinity to the 0. So what we're going to do in this video is we're going to talk about how we can solve these kind of limits in a different way than we've done so far. So the typical way that we've resolved these kind of limits is some kind of algebraic trick. There will be some algebraic tricks here, but typically we've done factoring. And what we'll see is that we don't need to do factoring for these, right? So one example that we have of an indeterminate form is sine of x over x as x goes to 0. So that's one where the numerator is going to 0, sine of x as x goes to 0 is 0, and our denominator is clearly also going to 0, but that limit is 1. Now we could pick a different limit that went to 0 or something else that went to infinity, but that gives kind of the broad idea of indeterminate forms. Okay, so there's this very convenient rule that says that if we have a pair of differentiable functions f and g around some point a, and we look at the limit as x goes to a of f over g, and it's either that f and g are both going to 0 or infinity, then, so long as the limit on the right-hand side exists, the limit as x goes to a of f over g is equal to the limit as x goes to a of f prime divided by g prime. Now, the first thing to notice, this isn't the quotient rule. This is the quotient rule for when you forget the quotient rule. This is taking the derivative of the numerator and dividing it by the derivative of the denominator. So, kind of, I don't know, kind of hand-waving, the reason why this kind of works is that you're looking how the numerator is changing versus how the denominator is changing. And what we would find is that when the numerator is, or when the whole limit goes off to 0, the denominator's changing and getting to its location kind of much, how do I want to say this? It's getting to where it should go much quicker. That's kind of what this is judging. It's judging the ratio of how the numerator is changing versus how the denominator is changing. And the other important thing to note, this only applies to 0 over 0 or infinity over infinity. If we have any of these other 5 cases, we have to manipulate our expression to get it into the 0 over 0 or infinity over infinity case, and we'll see some examples of how that works. Okay, so first we're going to go through these examples. So the first one is that we're going to have the limit as x goes to 1 of the natural logarithm of x divided by x squared minus 1. And what we can see here is that our numerator is going to 0, our denominator is also going to 0. So what we'll do is we'll say that we are using L'Hopital's rule by just putting an h over the equal sign. The other way we can do it is by using a 0 over 0, infinity over infinity, and I have that in subsequent examples. Okay, so when we use L'Hopital's rule here, we are saying that we are going to take the limit as x still goes to 1 of the derivative of our numerator, so 1 over x, divided by the derivative of our denominator, which is 2 over x. And we can simplify that a bit and get the limit as x goes to 1 of 1 over 2x squared. We now have a continuous function at x equals 1, so we get a final answer of 1/2. Right, so this tells us something where the numerator and denominator were both going to 0, but the limit came out to be 1/2. Okay, so the second one. So we could also, instead of just using the h above the equal sign, we could go and write the form that we're actually working with. So in this case, the 0/0. So let's go and take the limit as x goes to pi over 2 from the left of 2x minus pi, all divided by cosine squared. Our numerator is going to 0, our denominator is also going to 0. When we go and we take our derivative of the numerator, we get 2. When we take our derivative of the denominator, we get minus 2 cosine times sine, just from our chain rule. And then when we evaluate this as x is going to go to pi over 2 from the left, so we're in the first quadrant, cosine and sine will both be positive. Sine is going to 1, but the cosine is going towards 0. So we're going to have 2 over something that is negative and going to 0. So our entire limit is going to be minus infinity. So again, so we had something where the numerator was going to 0, the denominator was going to 0, and we got a limit of minus infinity. Okay, so for the next one, we can take the limit as x goes to 1 from the right of x divided by a natural logarithm of x. We'll go and apply L'Hopital's rule as before. We'll take our derivative of the numerator and get 1, and we'll take the derivative of the denominator and get 1 over x. We then get the limit as x goes to 1 from the right of just x, which is 1. No, there's a slight problem with this though. And this is why you need to make sure that L'Hopital's rule actually applies. So L'Hopital's rule only applies for 0/0 or infinity over infinity, and if you use it for something else, you're going to get a bizarre answer that doesn't make any sense. So if we come back to what we had our limit as x goes to 1 from the right of x over natural logarithm of x. Well, the numerator is going to 1, not 0. And the natural logarithm will be going to 0, and it'll be doing so from the right. So what we wind up with is 1 over a small positive number, which is going to give us infinity. So again, whenever using L'Hopital's rule, just make sure that you've actually got something where the form applies. So 0/0, infinity over infinity. Okay, so fourth example with the 0/0 or infinity over infinity case. So we have the limit as x goes towards infinity of x squared over e to the x. Well, as x goes to infinity, e to the x is going to infinity, x squared is also going to infinity. Now, this is one place where L'Hopital's rule becomes kind of useful, and we couldn't do anything before. So before, the thing we would always do with this would always be factor in some way. We can't actually factor anything here. So we'll have to use this L'Hopital's rule. So when we do that, we take our derivative of the numerator divided by our derivative of the denominator. So we get our limit as x is going to go towards infinity of 2x all divided by e to the x. Well, this is still something that is going to be of the infinity over infinity type because the numerator is still going to infinity, the denominator is still going to infinity. We take derivatives again, and we get the limit as x goes to infinity of 2 over e to the x, which is going to be 0. Okay, so that gives us kind of an overview of the first two cases, so the 0/0 or the infinity over infinity case. And then I'd mentioned that there are 5 other cases. So what we can do is we can just go and look at the general idea with these. And the idea is always take whatever form you've got and manipulate what you've got to get to 0/0 or infinity over infinity. Okay, so the first one. So we have the limit as x is going to go towards 0 from the right, so that natural logarithm is defined, of x squared times natural logarithm of x. So what we see here is that the x squared as x goes to 0 is going to 0, but natural logarithm as x goes to 0 is going towards minus infinity. So we have something that is of the 0 times infinity form. What we do with this is we go and we put something into the denominator, and we go and we flip, in this case, the x squared, and we write it as 1 divided by 1 over x squared. So what we've done is we've just kind of strangely rewritten x squared. But now what we have is we have the limit as x is going to 0 of natural logarithm divided by 1 over x squared. And now our denominator is 1 over x squared as x goes to 0, and that is going to infinity. So we now have moved our expression from being 0 times infinity to being infinity divided by infinity. And now we can use L'Hopital's rule. We get 1 over x all divided by minus 2 over x cubed. As x goes to 0 from the right, we get minus x squared over 2, and that limit is going to go to 0. Okay, so the next one. So we have 1 over x minus 1 over sine of x, as x is going to 0 from the right. So in this case, we have something that is infinity minus infinity. And again, we've had some cases like this before. We've had something where the limit has gone to infinity or maybe 0. Or I think we had one example where a limit like this went to something like 1/2. So what we'll do with an infinity minus infinity case is we'll go and get a common fraction. So we get our common fraction, we multiply the first fraction by sine over sine, we multiply the second one by x over x, and then we just combine. So we get a common fraction, we get everything down to one fraction. So we get the limit as x will go to 0 of sine minus x, all divided by x times sine of x. So our numerator is going to go to 0, sine of x will go to 0, x is going to 0, and our denominator is also going to 0. So we've now got our entire expression down into 0 over 0 form, and we'll apply L'Hopital's rule. So when we do that and we take our derivatives, we get cosine of x minus 1, all divided by sine of x plus x cosine of x. And this is something that's still going to 0. As x goes to 0, cosine will go to 1, and the sine will still go to 0, the x will go to 0, but the cosine will go to 1. So we'll get a numerator still going to 0, denominator still going to 0, so we'll just do L'Hopital's rule once more. And then we'll get minus sine of x all divided by cosine plus cosine minus x sine of x. The x sine of x part will go to 0, but the two cosines will go towards 1. So we'll get a numerator going to 0, a denominator going to 2, so our final limit will be 0. Okay, so that deals with what you want to do with the 0 over, or the 0 times infinity or the infinity minus infinity case. So fairly simply, manipulate what you have and get it into 0 over 0 or infinity, divided by infinity form. But now we want to look at what happens when we have something in the exponent. So for example, we have the limit of x going to 0 from the right of x to the x. So in this case, we have our base is going to 0, our exponent is also going to 0, and we just want to see what we do with this. Well, what we've said so far is that when you have a function of x that is sitting up in the exponent, you want to take the natural logarithm of both sides. So we'll say that y is this limit as x goes to 0 from the right of x to the x. We take the natural logarithm of both sides, and then we know that we're going to be able to pull the natural logarithm inside the limit. And then from our exponent rules for logarithms, we'll pull the x that's in the exponent out in front. We'll get the limit as x goes to 0 from the right of x times natural logarithm of x. So now what we've done is we've gotten our expression down to something that is going to be 0 times infinity. So we'll do as we did before. When we have infinity times 0 form, we'll flip something down into the denominator and proceed from there. One other thing to point out with these is that whenever you're flipping something into the denominator, you have two choices. You could rewrite this expression as x divided by 1 over natural logarithm of x. You would then have something that's going to be 0 over 0 form, but the rough idea is pick something that's going to make for an easy derivative. Finding the derivative of 1 over natural logarithm of x is not overly, it's not the simpler one to find. In this case, we're going to put the x into the denominator as 1 over x. So again, we've flipped x twice. So we've written it as 1 divided by 1 over x, which is just x. And finding the derivative of 1 over x is much simpler than finding the derivative of 1 over natural logarithm, so we'll pick x to put into the denominator. Okay, so when we do that, we get the limit as x goes to 0 from the right of natural logarithm divided by 1 over x. We've now got infinity over infinity form, so we'll use L'Hopital's rule. And when we do that, we get our derivative of the numerator is 1 over x, derivative of the denominator is minus 1 over x squared, and we'll then simplify to get our limit as x goes to 0 from the right is minus x, and that limit is 0. Now, the important part with this is what we found is the natural logarithm of y. So we found the natural logarithm of this limit, and now all that remains is just raise both sides to the e. So we know that the natural logarithm of y is 0, and that tells us that y has to be e to the 0 or 1. Okay, so final example here. So same kind of idea, we'll have the limit as x goes to 0 of sine of x over x all raised to the 1 divided by x power. So we have something where our base is going to 1. We know that sine over x as x goes to 0 is 1, and our exponent is going towards infinity, so 1 over x squared. We'll then go and take the natural logarithm of both sides as before, and then switch the order of taking the limit with the natural logarithm, and then use our rules for logarithms to go and pull the 1 over x squared out in front. So after some simplification, we get down to the limit is going to be x going to 0 from the right, because I forgot to put that in above. So the limit is x goes to 0 from the right of the natural logarithm of sine of x all over x, and then we have the divided by x squared in the denominator. So here we have the limit inside is going towards 1, so that would mean we would have natural logarithm of 1, which is 0. Our denominator's going towards 0 as well, so we have something that is 0 over 0 form. So we go ahead and we take our derivative of the numerator. We get our x over sine of x times the derivative of the inside part, which is x times cosine of x minus sine of x, all divided by x squared, and then the entire thing is divided by 2x. Now, one thing to keep in mind with these is that if you see things that can cancel, you should cancel as much as you can, because if you don't cancel, in this case you don't start canceling the x's, you're going to wind up doing much more work than you need to. So we'll go ahead and cancel off some pieces. So what we would have from this when simplifying is we'd have the limit as x goes to 0 of x times this x cosine of x minus sine of x, and it's all divided by 2x cubed sine of x. So we can cancel off an x from the numerator and the denominator, and we'll pull the 2 out in front just for simplicity. Okay, so then we have 1/2 times the limit as x goes to 0 from the right of x cosine of x minus sine of x all over x squared sine of x. So the numerator is going to go to 0 because the x cosine of x part is going to 0, and then sine of x is also still going to 0. And then it's all divided by x squared sine of x. So we'll have to go and pull out L'Hopital's rule once more. And when we do that, we get in the numerator, we'll get a cosine of x minus x sine of x, so just taking the derivative of x cosine of x with our power rule, or sorry, our product rule, and then we'll have a minus cosine of x from the derivative of sine. And then down in the denominator, we'll get a 2x sine of x plus an x cosine of x, so just taking the product rule again. What we'd see here is that the two cosines will cancel away, and then we could also get rid of these x's, and if we didn't look to get rid of those x's, we'd wind up doing much more work than we need to. So after those simplifications, we get 1/2 times the limit as x goes to 0 from the right of minus sine of x all over 2 sine of x plus x cosine of x. Unfortunately, we still see that this thing is going to be 0 over 0. The numerator is going to 0, sine of x is going to 0, and the x is going to 0 while the cosine goes to 1. So we'll just repeat and do L'Hopital's rule once more. We do it once more, we get 1/2 times the limit as x goes to 0 from the right of minus cosine of x, and then it's all divided by a 2 cosine of x plus a cosine of x minus an x sine of x. Fortunately, now we are finished because the minus cosine of x will go to 1. These cosines will also be going to 1, so we'll have a 3 down in the denominator. And then we have this minus x sine of x, which is going off to 0, but that's okay at this point. So this will tell us that our natural logarithm of y is going to be equal, after our simplifications, to 1/2 times the limit as x goes to 0 from the right of minus cosine of x over 2 cosine of x plus cosine of x minus x sine of x. That limit's going to is going to be minus 1/3. So we're going to have a half times minus a third, which tells us that the natural logarithm of y, so the natural logarithm of our limit, is minus 1/6, which says that the final answer is going to be that original limit we started with, limit as x went to 0 from the right, of sine of x over x, all raised to the 1/x squared power, is going to be e to the minus 1/6 power. Right, so again, so we see something where we had something in one of these indeterminate forms, and we got kind of a strange answer for the limit. Okay, so then one just kind of concluding comment that isn't entirely relevant to us, but it'll be really important when you go off to Calc 2 and you start doing things with sums, is to just look at how things grow as x goes off to infinity. So we'll just use a double greater than sign to say that g is much, much bigger than f as x goes to infinity. So g is growing much faster than f. So what we'd have here is that a polynomial term, so an x to the p, is going to grow much faster than any natural logarithm. The natural logarithm is about as slow of a function as there is. An x to the p times some natural logarithm is going to be bigger than just a regular polynomial part of the same power. But if you gave me an x to the p plus some s, so some you gave me a bigger polynomial power, that would go and beat the smaller polynomial with the natural logarithm tacked on. Then what we have is that if you go and start powering up some number, it'll be bigger than a polynomial. And then lastly, you get an x to the x. So you take some number, you power it up by itself x times, that'll be bigger than just a regular base raised to the x. Again, this isn't something that's totally necessary here, but it'll be useful when you get off to Calc 2 and start doing particularly series work. We'll mention a little bit about series in the next video, and then you'll come back and see them more again in Calc 2. Okay, so I think that covers everything that we need to see for this, so I will see you all next time.